All right, let's talk about one of the most iconic molecules in organic chemistry, benzene. We all know it's the super stable aromatic ring, but what's really fascinating is that this stability hides a kind of split personality. You see, under the right conditions, it can be a generous electron giver, but in others, it becomes an electron taker. So let's dive in and really get to know these two faces of benzene. So here's our game plan for today. We're going to start with why benzene is so darn stable in the first place. Then, we'll meet its first personality, where it acts as an electron giver in electrophilic substitution, and we'll learn the rules that tell those reactions where to go. After that, get ready for the plot twist, its second face in nucleophilic substitution. And finally, we'll put it all together to see how chemists use this stuff in the real world.
Okay, so first things first. Let's talk about benzene's core identity. It's famously unreactive. This incredible stability all comes down to its aromaticity, that continuous, delocalized cloud of pi electrons that's shared over the entire ring. Think of it like a protective force field that makes the molecule exceptionally stable and really resistant to any reaction that would try to break it.
Which, leads to a pretty big question. If benzene has double bonds, why doesn't it just react like a normal alkene, like cyclohexene? Why does it get to play by a totally different set of rules? And this slide right here is the answer. Alkenes, they undergo addition reactions. The pi bond breaks, you add stuff across it, easy. Benzene, on the other hand, says no way. Breaking its pi system means losing all that amazing aromatic stability, and it will do anything to avoid that. So instead, it undergoes substitution. It just swaps out a hydrogen for a new group, keeping its precious aromatic core perfectly intact. So this brings us to benzene's first personality. Face number 1. This is where it acts as an electron giver, or what we call a nucleophile. Now, even though that ring is super stable, that electron-rich pi cloud can be tempted to attack something that is really electron deficient, a strong electrophile. And the name for this reaction is Electrophilic Aromatic Substitution, or EAS. Honestly, the name tells you the whole story. An electrophile, an electron lover, attacks the aromatic ring, and a substitution happens. In this dance, the ring uses its pi electrons to do the attacking, so it's our nucleophile. But there is a catch. Because benzene is so stable and happy on its own, it won't just react with any old electrophile. You need a strong catalyst, usually a Lewis acid, to generate a super reactive, really angry electrophile. You have to make it so electron poor that the benzene ring finally can't resist the urge to attack it. Now, in EAS, there are a handful of reactions that are really the foundation of everything. Let's start with the first 3. You've got halogenation, which sticks on a chlorine or bromine. Then there's nitration, which adds a nitro group, super important in synthesis. And finally, sulfonation, which adds a sulfonic acid group. The other essential reactions are the Friedel-Crafts reactions. These are amazing because they form new carbon-carbon bonds. Alkylation adds a simple carbon chain, but has one big annoying problem. The carbocation intermediate can rearrange itself, which can mess up your product. So to get around that, we use acylation. It adds an acyl group, and because its intermediate is stabilized by resonance, it doesn't rearrange. It gives us way more control. Okay, so we know what we can add to the ring, but what if there's already a group on it? Where does the next one go? Well, it's not random at all. There are rules, and the group that's already there is the director. It's in charge of the whole operation. These directing groups control whether the new substituent attaches at the ortho, meta, or para position. Think of it this way. Ortho is right next door, meta is 1 carbon away, and para is directly across the ring. This table right here, this is basically your cheat sheet for predicting what happens in EAS. We can lump these groups into 2 main camps. First, you have the activators. These are electron-donating groups like OH or alkyls. They make the ring even more reactive, and they direct new groups to the ortho and para spots. Then you have the deactivators. These are electron-withdrawing groups, like a nitro group. They pull electron density out of the ring, making it less reactive, and they direct to the meta position. And the halogens? They're the one weird exception. They're deactivating, but they still direct ortho and para. So what happens when you have 2 groups already on the ring, and they're pointing in different directions? Who wins? The rule is actually super simple. The strongest activating group wins. It has the most say over the ring's electrons, so it calls the shots on where the next group has to go.
And now for the big reveal. Benzene isn't just a giver. Under the right, and I mean very specific conditions, it can completely slip its personality and become an electron taker. This is phase number 2, where benzene acts as the electrophile. And this table just lays it all out perfectly. In nucleophilic aromatic substitution, or NAS, the roles are completely backward from EAS. The ring is now the electrophile, meaning it's electron poor. The attacker is a nucleophile, and you absolutely need strong electron withdrawing groups. And maybe most importantly, the leaving group isn't a tiny proton anymore. It's usually a halide.
The big takeaway here is that NAS has some really strict requirements. It won't just happen. You need 3 things: a strong nucleophile, a good leaving group already on the ring, and at least one powerful electron withdrawing group, like a nitro group. And that withdrawing group has to be in the perfect spot. It must be ortho or para to the leaving group so it can stabilize the negative charge that forms during the reaction. This explains one of the wildest things about NIS. Fluorine, which is normally a terrible leaving group, actually works great here. And you might be wondering why. It's because the slow step, the one that determines the reaction rate, isn't breaking that super strong carbon-fluorine bond. It's the initial attack of the nucleophile on the ring. And fluorine's crazy electronegativity makes the carbon it's attached to extremely electron poor, which actually speeds up that critical first step. So let's see how this all comes together. Knowing the rules for EAS and NAS isn't just for passing a test. This is the foundation for actually planning how to make complex aromatic molecules. It's like a logic puzzle, and now we finally have all the pieces. Take a look at this puzzle. We want to make metachloroaniline, but wait a second. The chloro group is an ortho/para director, and so is the amino group. So how on earth do we force them into a meta relationship? At first glance, it looks totally impossible, right? Well, here is the absolutely elegant solution. The key is to use a temporary directing group. We start by nitrating the ring to add a nitro group, which is a strong meta director. Then we add the chlorine and boom, it goes exactly to the meta position. For the final step, we just reduce that nitro group into the amino group we wanted all along. It's just a beautiful piece of strategic planning. And that synthesis problem brilliantly proves the single most important rule in this whole game. The order of operations is everything. Choosing which group to add first, second, and third completely changes the outcome. And as you get deeper into this, you learn even more powerful strategies. For instance, you can dodge those pesky Friedel-Crafts rearrangements by doing an acylation first, then a reduction. You can use protecting groups to temporarily mask a reactive part of your molecule. Or you can even use a removable blocking group, like a sulfonic acid, to force a reaction to a specific spot and then just pop it off later. It's all about chemical strategy. So there you have it. Benzene really does have 2 distinct faces. It's an electron-rich giver, reacting as a nucleophile through EAS, and it can be forced to be an electron-poor taker, reacting as an electrophile through NAS. Understanding this dual nature and all the rules that govern each personality, that is the absolute key to mastering aromatic chemistry. You now have the fundamental toolkit for aromatic synthesis. You know the reactions, you know the directors, and you know the strategies. So the only question left is, thinking about the order of operations and the 2 faces of benzene, what molecule are you going to build next?